Welcome everybody. This is a fantastic opportunity for a Geotalk. We are joined today by our colleagues and friends from Helmholtz Institute Freiberg from HDZDR, which I will not butcher by trying to say.
It's good enough.
Here we go. So today we're going to be hearing about big data techniques for hyperspectral core logging by Sam, and who did his PhD at Monash in Australia, and since then joined Helmholtz in Germany, and for the past about 2-3 weeks has been running around South Africa, scanning lots of rocks, scanning lots of deposits. And
dodging the rain of the wet season.
Dodging the horizontal rain. And yeah, hopefully we'll see what you plan to do with all this big data.
Yep.
Fantastic. Cool.
Good. Thanks, Leo. Thanks you all for coming. It's good to see quite a few faces here. I was told it's not the best time of year, so that's good. I'm going to present today a bit of an overview, I guess, of work that's been going on at the HIF in Germany under Richard's group for the last probably almost 10 years now. I've been involved for the last 5 years or so, and a big part of this, a big part of what I'm going to show today has been done in the last 2 years as part of this EU vector project, where we tried to really push what we can do with hyperspectral drill core scanning to the next level. So I'm going to assume, first of all, that some of the people here haven't done much with hyperspectral data before. So the first part of my talk will be a little bit of an overview of what is hyperspectral data, what can we do with it, and sort of how to a little bit. Then we'll transition and I'll talk a little bit about what we've been doing with drill core scannings, some of the common challenges associated with drill core scanners, and also our solutions to those and what we think this unlocks. And based on that, I'll finish up by talking a little bit about where I see this going in the future, specifically trying to convince you that I think that hyperspectral data, hyperspectral drill core data is most useful if you acquire it straight away, as soon as you can after drilling, so that you can use it through your whole exploration workflow, and also so that you have the data while you still have the rocks there with you, easily accessible. So we'll come to that. So hyperspectral data. We all know that light is a continua, is a spectra of different wavelengths or energy levels. And most of us here will see in 3 colors in the visible range, the red, the green, and the blue. But there is a lot of light bouncing around in different wavelength ranges. Bees, for example, can see in the ultraviolet as well, and so they see a very different world to what we see today. If you go underwater in the tropics, there's a really, really cool little shrimp about this big, and for some reason that no one fully understands, he can see in 12 different colors. So they have, again, a completely different experience of the world because they have this multispectral vision. We're now able to replicate this using cameras, essentially. So everyone here will have their RGB camera in their phone that takes images which have 3 channels or bands, the red, the green, and the blue, as you can see here on the left. But if you use different detectors and different types of optics, you can capture light in different wavelength ranges to build what are called multispectral images. So many of you will have heard of or used ASTA, for example. It's a prime example of a multispectral imaging satellite which collects information in carefully chosen wavelength ranges such that different minerals or different vegetation types come up in very different colors. If you push that to the extreme, you come to what we call hyperspectral data. So this is where you have a camera which acquires typically hundreds of separate bands. The camera we've been using here has about 400 bands, and these are very, very narrow bands and closely spaced, so that you end up acquiring what you can see in the bottom right here for you, a spectra for every single pixel. So that's sort of the amount of energy entering the camera at each wavelength range across the the area that it's sensitive at. And the reason that this is useful, of course, is that each, many different minerals or plants or so on will have distinctive characteristics in this spectra that we can use to identify them. These characteristic features, or absorptions as we tend to call them, occur because the light that hits a crystal structure, a mineral, will be absorbed by typically covalent bonds at very, very specific energy levels. And so there are certain bonds in minerals that you're able to essentially identify because you get a drop in the amount of energy that is reflected due to that absorption. Different minerals require different wavelength ranges. So typically in geology we work with the visible near-infrared to shortwave infrared, which is good for iron oxide minerals and minerals that contain hydroxyl groups, so clays and micas and so on. Then if you go slightly into longer wavelengths, into the mid-wave and the long-wave infrared, you get to a region where you're able to see the silica to oxygen bonds, which means that you can start looking at a whole bunch of different silicate minerals. I'm not going to go into much depth here, but I like to put this in because it's a really, really good place to start. If you're interested in how you can apply hyperspectral data to mineralogy, this is a really good paper to give an overview of how different minerals manifest in hyperspectral data. The key thing to note here is that down the left-hand side, you have all of the different functional groups that you sort of can detect that absorb energy at certain wavelength ranges, and the different wavelength ranges in which you would expect to see those. What's not shown here, and is actually really important and really cool, is that the cations that are bonded to those functional groups change the energy level at which light is absorbed, which means that you get systematic shifts in the position of the spectra that can help you distinguish, for example, iron-rich from potassium-rich clays. And so you can use these very, very specific changes in the wavelength position to map minerals that are very difficult to distinguish using other techniques. It also means, and it's also very important to remember, that we're not seeing the whole crystal structure like you might do with XRD or something. We're just seeing these specific groups. And so there's often multiple solutions for one spectra. There could be several different minerals or mixtures of minerals which will manifest in the same way. This means that hyperspectral's, I guess, less accurate than many lab-based techniques. You know, XRD will be able to give you, for many minerals, a fairly good quantification of what's there. Hyperspectral can't do it to that degree of accuracy, but what it can do is do it remotely without any sample prep and across a huge range of scales. So I think one of the really unique things here is that these cameras, you can put them in a lab, in a drill core scanner, like we'll be talking about today, but you can also put them on a tripod. That's what we've been doing for the last 3 weeks or so, to take maps of mine pits or outcrops or cliffs. You can put some of them on drones when they're light enough, and then you can sort of acquire aerial imagery of small areas. Scaling up a little bit, you can obviously put them in aircraft as well then to acquire much larger areas. And very recently now, for the last 3 years or so, we've had hyperspectral cameras covering the wavelength range which is relevant for most geological applications in space. So we're now getting close to having global coverage with satellite hyperspectral data as well. And this is all pretty much the same technique, fairly similar cameras, so you can use this as a tool to bridge scale gaps. You can acquire data in a lab to see what my minerals look like, and you can use that information to then look at the satellite scale to see, for example, what the distribution in space might be. It's important to remember, though, especially if you're thinking about buying drill core scanners, that the data that comes out is this big, huge block of an image. So it's a data cube, it's an image which has 2 spatial components and 450 to 900 bands, depending on what cameras you're using and so on. And all of the information is within that, but depending on your application, depending on what minerals you're looking for, depending on what you're trying to do, how you get that information out and you turn it into something useful for geology is a bit different every time and can be quite a challenge. So acquiring the data might be even relatively easy once you have a system up and running, but then doing something with it is always a bit more difficult. So I'll quickly run through now some of the common analysis techniques just to give you an overview. I won't go into any depth, and then we'll go on and talk about drill core scanning. Probably the most conventional thing done with hyperspectral data is what's called spectral matching. this has been done for a very, very long time, and you build a spectral library. So you have a library showing this is a spectra of biotite, of muscovite, of so on and so on. And then there's various different algorithms which compare those spectra and say, my pixel is most similar to this one, so therefore it must be quartz, or it must be muscovite, or it must be biotite. This can work fairly well, but it's got some very, very important caveats to be aware of. Firstly, it's only as good as your spectral library. And unlike things like XRD, hyperspectral data is influenced by lots of different things. So your library typically needs to be site-specific. You can't have a muscovite from one place and expect it to be exactly the same as a muscovite from somewhere else. Secondly, this is a classification algorithm, and we're acquiring data in a drill core scanner, which is sort of the highest resolution technique you commonly use, at roughly 1 to 2 millimeters per pixel. And for many rocks, I would say possibly most rocks, even at 1 millimeter scale, you're talking about a mixture. You won't have a pixel which is just one mineral much of the time. So you need to be a little bit careful with that. Something else which is quite commonly done and is very, very powerful. This is, I think, one of the more powerful things that you can do with hyperspectral if you have the right type of problem and you have the right sensors and the right mineralogy, is called minimum wavelength mapping. So this is where you map very accurately the minima, the position of this energy absorption. And as I mentioned earlier, that can tell you a lot about what cations are in your crystal lattice. And so this is how, for example, you can distinguish dolomite from calcite by looking at the position of the absorption feature associated with carbonate, or you can distinguish whole groups of different clay minerals by looking at this variation in the position of different absorptions. It doesn't give you a quantitative estimate of how much of that mineral there is, but it can start to distinguish different mineral groups in a really powerful way. If you're interested in more quantitative data, so estimating mineral abundance, it's fairly common to do what's called linear unmixing. This is a little bit similar to what you might do with XRD, for example, where you have n-member spectra for your pure phases and you find a way of doing a linear sum of those to reproduce your observed spectra. And then the weights in that linear sum correspond to your mineral abundances. This sounds very good in theory, and in a linear system, the maths is actually fairly simple. It's very easy to do. The problem comes in when you start working with real rocks, is that the spectra that you observe will not actually be a linear mixture of its components. So there's lots and lots of sensitivities in there about how the light interacts with the different minerals, the grain size, the porosity, the surface roughness. All of these things will influence which minerals influence the spectrum more than others. And so if you do a linear unmixing, you can get useful results, but it won't be the same as how much of that mineral is there. And lastly, and this is something which people have been doing, I guess, more and more recently, you can treat this as a regression problem and acquire training information using, for example, an MLA. So you have training mineralogy information. You acquire co-registered hyperspectral data over that, and then you can train a machine learning model to say that if I see this spectra, it means I have this abundance of mineralogy. This is a surprisingly difficult thing to do, especially if you treat it as a regression problem. I've torn my hair out about this for quite a long time, because you have typically 400 to 1,000 dimensions as the input to your regression. And in a mineral project, you might have 20 different minerals that you care about or more. So you have many things coming out of your regression problem. And so it's a bit of a monster of a model. But there are ways to do it. And if it's done well, it can give you really, really nice quantitative mineral maps that if you validate carefully, you can start to become relatively confident in. But you do need to validate it, because these models get tripped up all the time. So that's an overview of what hyperspectral data is and what we tend to do with it. I'm happy to, in questions later on, talk about those methods specifically, but that's a nice overview of where we would normally start. I'll transition now to talk about drill core scanning specifically. So this is an example of a drill core scanner. This is the one that we use, the Spec Im Sisu Rock. Inside this cabin here, you can see 3 different hyperspectral cameras, because unfortunately there's no single camera that can measure the entire wavelength range that we care about with rocks. Normally you have one for the visible near infrared and the shortwave infrared, so that's good for clay minerals, iron oxides, chlorites, phyllosilicates. Then a separate camera for the midwave infrared and a third one for the longwave infrared. And you need those latter 2 if you want to start looking at silicate minerals. None of these can see sulfides either. I'll put that out front and center. That's something to be aware of and something which is unfortunate. But the really nice thing and a big difference to other types of scanning devices is that you can scan quite a lot of core with these instruments. So if you have a good team, you can get through 1 to 2 kilometers in a reasonably civilized workday. If you work 24-hour shifts, I'm sure you could get a lot more than that. The core stays in its box. You don't need to take it out. You don't need to move it around. You do need to spend a bit of time preparing it, of course, because you want it to look nice and pretty. But you don't need to place it in a separate device and put it through the scanner. And because it's an imaging technique, unlike a line scanning XRF or something, you get an image of the entire core that's exposed. So you get a more representative sample, I guess, than a single line along the core axis. But there's a catch. There's always a catch. Every image from every one of those cameras is about 1 gigabyte, roughly. So we've got 3 cameras. You get about 3 gigabytes of data per box of core. So if you're then scanning for a full day, you get well over 1 terabyte of data, which can be quite hard to manage and handle and store and so on. It adds up very, very quickly. On top of that, the camera gives you a raw image of radiance, more or less. And you need to correct that to estimate the reflectance, so the material property, the spectra you're interested in. Typically, you want to co-register the different images from the different sensors, because otherwise you can't compare the pixels from different spectral ranges. You need to mask the images to say, this is rock, and this is plastic, and this is a meter mark, and this is a piece of wood. That keeps us very busy. And then you need to figure out how you're going to store all of this information, organize it in a way that if you're looking for box X in drill core Y, you can find it. And often then you will mosaic them into ways that you can visualize entire boreholes at once as well, of course. So if you have a look here, I've sort of built a little chart showing that there's quite a lot of stuff that goes on or has to go on before you get a product that you can use to make decisions, to see what's going on, or to understand something about your geology. So this was a big part of what we wanted to do as part of this vector project that I mentioned, was to say we've got all these challenges. We've got big data. We need to figure out how to mask the cores, so we're looking at the rocks rather than stuff around the rocks. We need to line up the data from the different sensors onto the same grid so that we can get a continuous spectra from the V-near to the long wave. Need to figure out ways of analyzing this such that we get relevant information for whichever particular deposit or site we're working on. And we need to be able to do this in a way that you want to inevitably integrate this information with other sources of data. So that's another co-registration problem. You need to take your hyperspectral data and line it up with downhole geophysical logs or assays and so on. And you need to have quite good depth information to be able to do that. And lastly, if you think about what this is an image of your drill core at millimeter resolution, which means it's an image which is about 5 centimeters wide and kilometers long. So it's quite a fun visualization problem when you think, what do you do with that? And what we've tried to do, and what I'll now show, is to say, if we can automate a lot of this workflow, if we can automate most of this, then we can start to get at least some preliminary results on the hyperspectral information while we've still got the core boxes in front of us. And that is really important for 2 things. One, it helps us to check the data quality. So that's something I didn't mention, but often if you set these sensors up wrong, you collect rubbish data. So it's important to be able to check the data quality. And also it means if you're able to do some form of even preliminary hyperspectral interpretation, you can have a look at the rocks and you can check. If the hyperspectral data says, hey, I've got carbonate minerals here and you're not expecting it, it's much easier to be able to do that if the core's out on the core rack than if it's been put away in storage somewhere. And so what we've done is we've put together a Python software tool, which is it's open source, so you can find it at this GitHub link if you're interested. And I won't go into any depth, but basically this runs on a server, on a computer that we have in the scanner, and it just sits there permanently looking in an input directory for new data that's been put in there from the cameras. So the cameras acquire an image, they write it in this folder, and then Crunchy picks up that file. Based on what type of file it is, it runs all of this pre-processing stuff that you don't want to care about, puts it in a standardized output format, and because that output format is standardized, we can actually serve that through a web server so that you can be standing with a tablet in the core shed, and within 1 to 2 minutes of core being scanned, you can see the results starting to come out. Just as a side note, I call this real time because it takes 2 minutes or so to process a scan, and it takes about 4 minutes to actually acquire that scan. So we're able to process faster than we can acquire. A really key part of this is obviously having a consistent way to store that information. So this is the sort of second software tool that we've built. I call it HiCore, and it's kind of a database. It's a directory structure which has a standardized Python interface that helps you put your data so that it's the same always for all of the boxes for all of the holes, and also manages a lot of standardized operations that you want to do. If you want to do parallel processing, if you want to put all of your images in a nice mosaic, things like that, that's sort of built into this data structure. I need to say at this point that there was one thing that we couldn't automate well, and that was saying what's a rock and what's not a rock in the image of your core box. We can get this working quite well for specific projects. So if everyone used the same type of plastic core box, then it would be really easy. But you go around the world, people use all sorts of different things in their core boxes, and people have all sorts of weird ways of marking meters, and there's just so much variability that while we have a solution which is relatively generic and is quite good at giving a first guess at what is core and what's not, at this point at least we always check it manually and typically have to change it a little bit, especially because some of the things I'll talk about later, often you're interested in what are the weird things in your spectra. And if you have a piece of plastic, for example, on your rock, that always comes out as being a really weird mineral, because it is. So the masking is a very, very important step. Because this is a bit interactive, we've built a GUI, a user interface tool called Nappery Hippo. You can have a look at that there. That can help with this sort of masking. And I've also seen recently a guy at the Irish Geological Survey has also built quite an interesting looking sort of user interface for doing a lot of this basic processing on hyperspectral drill core data. So if you ever come across this data, two different things to have a bit of a look at. Lastly, as I mentioned earlier, once you have all of this, so once you've gone through this processing workflow, you've put everything in your nice standardized format, then it's computer readable. So we can build web apps, for example, that lets you navigate through your core database, see different data products that have been generated from the hyperspectral data, look at mosaics of individual drill cores and so on, and even in this case, load, because we guess the depth of the drill core based on the meter marks of the box, load auxiliary data like assays or logging codes so you can start co-registering everything and looking at it together. Because that's where the real power of this information comes in, is if you can line up the hyperspectral information with some form of other information while you're looking at the rock, then you can make the best decisions. If you're interested in this, I've put a QR code up there that will take you to this visualization platform that's live. You can have a look and a play. Don't use it on your phone though. So you can take a picture of this, but then copy the link and have a look on your laptop. It's not very mobile friendly. Oh, do you want the QR? Yeah. So to summarize, I guess, the automation or development stage of this, we've now managed to automate almost everything here except for the masking. And hopefully soon the masking problem will be solved as well, meaning that within 2 minutes of scanning the drill core, you can have this nice web visualization platform where you can be doing your core logging while using all of this auxiliary information. And to wrap up here, I guess I'll now think about what this means. What can we do with this? Why do I think this is useful? The obvious thing is if you can put this in the hands of your geologists while they're logging drill cores. So, geologists are fairly good at noticing subtle things about rocks and making decisions on what lithologies or alterations there are. But if you can put something in their hands that lets them see well beyond the visible range and start integrating this information on quite minute details in clay mineralogy, for example, then I think you can very quickly make much better decisions while you're doing the logging. It is a good way to focus geologists' attentions on things that might be a bit weird. So something that we've discovered while doing this is that often you do the hyperspectral imaging and then you'll get something coming out that you're just like, that's strange, I can't explain that, what's going on here? If you just have the hyperspectral data alone, it's quite difficult to answer that question. But if you're able to then, based on that, go to that location, potentially sample it, potentially have a look at the rocks and decide what's going on, then it's a nice way to say, hey, there's something there, have a look. Similarly, if you get something wrong in the types of analyses that you're doing and say you're logging stuff and you get a very unexpected mineral coming up, then it's good to be able to check that straight away because maybe you need to change how you're processing the data or maybe you've come across something that you weren't expecting. Either way, much, much better to be able to do this while you've got the core right in front of you rather than to have to get it out of storage. And this is something that's potentially a bit more subtle, but I think that because it gives you a much better overview of the variability that you have in an interval of core, you can use that to make better decisions about sampling. So you can better sample the mineralogical variability, you can better pick contacts that you might want to use to separate different composite intervals, and sort of offset a little bit the typical geology bias of always going for the shiny stuff. To take that to the extreme, we've been playing around with different ways of actually automating the sample selection. So this isn't something that will work all the time, but if you're interested, for example, in saying, I want to build a representative sample set showing the mineralogy of this drill core, then you can run the hyperspectral data. You can use various unsupervised machine learning techniques to look at the variability of all of the spectra in your drill core and say, these are my end members, these are my extremes. They will tend to be pure mineral phases that are sort of the unusual spectra, if you like. Or you can do clustering to say, this is group 1, and you should sample here if you want to have a representative sample, and this is group 2, you should sample here if you want to have a representative sample. And because this is imaging data, because it's spatial, you can even run say a thin section sized virtual sample across your entire drill core and say, where can I put this to capture the most information? And this is something that we actually tried using when we were trying to acquire training samples for MLA to do mineralogical predictions from hyperspectral data. This is coming back to the masking. This is where you need to have a very good mask, because the first time we did this, it would always pick the plastic, the weird things that someone had thrown in the drill core, and it was a nice demonstration that it was working. It was finding all of the end members, the unusual stuff in your drill core. It just wasn't really what we were looking for. And then the final thing that I think this is quite useful for, and this you have to change a little bit about how we think about hyperspectral data, but because it's really easy to acquire, you can acquire it at lots of different scales, you can kind of use this information as a glue to glue together all sorts of other pieces of information. So this is an example. If you can scan a drill hole, so then you have millimeter resolution hyperspectral data over your entire drill core, you can then select your samples for an automated mineralogy, for example, or an XRD or some other sort of analysis, and also scan those samples with the hyperspectral instrument. So you have some information then linking the results of that mineralogical analysis to the entire drill core and comparing this part of my drill core, how similar or different is it to my sample. taking this in a slightly different direction, you can also do this with physical or petrophysical properties. So if you sample your drill core and you do uniaxial compression tests, you can also acquire a spectra for those samples, and that spectral can be used to say that these rocks here are similar to the rocks where I did my compression test, and these rocks are very, very different. In the extreme level, you can use then this information to build regression models, to build machine learning models which can predict or upscale your mineralogy across an entire drill core, or also pretty much any other property that you can measure that you think may be related to the hyperspectral information. Just to expand a little bit on this, so as part of this project we did quite a lot of mineralogical upscaling. So we did several hundred MLA to build a training database of the mineralogy of 3 different deposits, and then trained multi-layer perceptron models to predict the mineralogy based on the spectral information. This is a very overwhelming plot. Don't get off-put here, but I just wanted to show it because it shows very nicely that we can very accurately predict your abundant minerals, so things that are present more than about 5% modal abundance, and typically you can get those fairly well. And then it very quickly gets very, very hard once you start going below about 5%. And unfortunately, often it's the minerals that are less than 5% modal abundance that you actually care about the most. But for your rock-forming minerals, for example, then it's been working really, really nice. The other thing that we've done, and this is a little bit novel, a bit innovative, is we've started trying to predict things other than mineralogy. So traditionally, everyone's thought about hyperspectral data, at least in geology, as being something useful for predicting mineralogy. But I mentioned earlier that the spectra that you get is also influenced by porosity, by grain size, by surface roughness, and these, when combined with mineralogy, are all sort of latent features that influence a lot of mechanical properties. So we did an experiment where we've taken several hundred uniaxial compression test samples, so we know the strength and the Young's modulus of these rocks from a compression test, and then we scan them with the hyperspectral scanner, and then we train a model which essentially tries to learn from the hyperspectral information how to translate all of this mixed up signals from grain size, mineralogy, porosity, and so on to predict the strength of the rock. And that's actually worked really quite well. We get regression coefficients of about 0.7, meaning we think, and this is something we still need to do, but we think that you can take a model like this and apply it in the same way as you do traditional mineralogical upscaling. And then you might get for your entire drill core, a prediction of the uniaxial compressive strength or something like this. And this is something that we see as being really, really useful in the world of geometallurgy, for example, where you can start to build deposit models that aren't just chemistry, but you can add a mineralogy layer and a layer of how strong the rock is and start acquiring a lot more information to really, really tie down these other properties. Finally, just to touch on this very briefly, I can't talk about drill core scanning the entire time. We can also take the scanners out of the camera and put them on tripods, which means you can do all of the things we've just been talking about, but on mine faces, for example. So this is an example from an old tin tungsten deposit near Freiberg, which also happens to contain a huge amount of lithium, so people are now very, very interested in it. And we're able to go there and acquire a hyperspectral image of the mine face and actually turn that into a prediction of the lithium grade. You need to be a bit careful about which problem you choose to do this with, but there's a lot of things that it could be really, really useful for. So to wrap this up, I hope I've managed to convince you a little bit that hyperspectral data is useful, A, and B, that if you can acquire it early, so as soon as possible in your exploration workflow, essentially, it helps you to make better logging decisions, first and foremost, better sampling decisions, and also, sort of going in the other direction, it helps you make better use of your hyperspectral data because you can test and validate hypotheses and compare things with the rocks while they're right in front of you rather than doing it on your desk 3 months later when it's much more difficult. And with that, I think I'll leave it here. Everything I've talked about here is open source or open access, so there's a whole bunch of links there you're welcome to have a look at. All of the Python codes are listed at the top. I've written a bunch of tutorials that you can use if you're getting into Python that you can sort of use to learn a little bit how to do this. I've also put some demonstration data sets up there that you can have a look at if you're interested. And then last but not least, if you're interested in doing sort of more commercial things rather than more research things, then we also have a company that you can talk to do this as a service rather than as a research project. Good. Questions? Please.
It sounds like.
I take this off? Yeah.
Unless you want to sit on his lap.
It sounds like mainly this stuff is applicable to secondary minerals. But to be most useful to us around here, we're going to want to be able to distinguish things like olivine from two different kind of pyroxenes, from two different kind of feldspars, from three different kind of iron titanium oxides. Sulfides, you said forget about it, okay. But those minerals that I mentioned are the ones that we looked at mainly, and we don't care too much about the secondary stuff.
Excellent question. From the traditional applications of hyperspectral, you would be right. So most people acquire Venia and shortwave infrared information where you don't see much variability amongst the silicate minerals that you were talking about. Once you have the long-wave infrared, which a lot of scanners do, then you can start to distinguish your pyroxenes and your olivines and your feldspars. So you do get information on your rock-forming silicates then. I will add to that we've been looking at a lot of bushveld rocks over the last few weeks, and there were a hell of a lot of secondary minerals in those. And I think that those secondary minerals also tell you a lot about the primary minerals. So you can often make inferences about what the primary silicates are or were based on which secondary minerals you start getting replacing them, especially in sort of weathered environments.
Can you give us an example of what secondary minerals you found that tells you about what primary minerals?
So I haven't looked at the data enough to be able to say specifically, but we have seen a lot of variability in clay mineralogy. In clay mineralogy, and that seems to be, it has the same spatial structure as a lot of the different layering. So there is something in that which, perhaps based on the iron content, for example, you're getting different clays forming in different settings. But we acquired the data last week, so we'll need a bit longer.
I don't know, to me, when we see clay minerals, we want to run.
Yeah, I can understand that.
Thank you, Sam. That's really fascinating and just highlighted how complex this is, right? You can't just get a core scanner and decide to scan core, which I think is a very tempting thing to want to do for many different people. I was just wondering what the opportunities are, and I guess it speaks a bit to Lou's question as well, and we've spoken about it before, is what are the opportunities for starting to think about getting semi-quantitative, quantitative chemical data alongside as you scan for the hyperspectral data? Is that something that's just too complicated, or is it something that you can start to do, but you obviously then need to cross-reference with assay data or some other form of analysis? Yeah, but which is also, quantifiable. I'm thinking about libs as well.
So one thing that I think would be really fun to do and quite doable is if you scan a box of cores, it's processed, and then some of these automated sampling algorithms essentially say you should think about acquiring XRF spots here, 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 and here, so that then you're covering the variability in your drill core to some extent, at least from the hyperspectral data's perspective. And if that information is all co-registered nicely, then you can use the hyperspectral to try and expand outwards from your XRF points. So then get some sort of continuous proxy or estimate of what your chemistry might be doing.
So what about the microphone? Do you think there's a future where you could be obtaining quantitative, semi-quantitative geochemical data at the same time without making
Certainly, yeah. You're probably not going to have a full imaging system, but you can acquire, you know, a large amount of data along your cores, say, and then integrate that. That's certainly doable.
Is there a way to integrate the XRF and the camera, like sit next to each other so that you can acquire both at the same time?
You can put them in the same scanner. I mean, you wouldn't put them in the camera, but already this scanner is a cabinet with a whole bunch of different sensors in a conveyor belt, and the conveyor belt is going underneath, and you can add stuff to that. Or we're also playing with putting these instruments on robotic arms, for example, so that they can swing in and do stuff while you're... And that's essentially what a lot of these XRF scanners are as well. It's sort of a robotic arm that moves along the core and acquires the data. Paul, are we giving up on the microphone, or?
For the people online.
If you're going to start using this in a sort of exploration or evaluation scenario, presumably you're going to have to start talking to sort of representatives from things like CRISCO 43101, etc., in terms of, is this acceptable, is this auditable compared to an assay, etc., or not. I mean, I don't think it will ever replace assay, but it potentially is going to replace some of the sort of geological expertise in terms of core logging. And at the moment, CPRs do have to say things about how things were logged. Auditors do have to say, was it logged appropriately? Was my CPR okay? Are you intending to start to talk to people from the sort of various organizations that deal with that sort of thing?
That way up? That way up. That way up. No, it's that way up. So I'll say first, I completely agree. I don't see this ever replacing assays, for example. And I actually don't see it replacing core logging either. I think, you know, having geologists look at the core is really important and really useful. The job of our job here, the job of hyperspectral, is to give them more information so they can do that better. Should these codes be updated? I think probably yes. Especially when you start talking about sort of building deposit models that are more than just chemistry. So if you want to build deposit models that have information on mineralogy and so on in them, that's where hyperspectral is really powerful. It's also where you can make really big mistakes, and you can certainly get things very, very wrong if you're doing things in the wrong way. So that's where updating codes would be useful. But to my knowledge, and this isn't my area at all, but to my knowledge, the codes don't really talk that much about mineralogy. It's very much on getting the chemistry right. And so sort of it's part of that broader problem.
Hi, thanks. Obviously, hyperspectral core logging has been around for a long time. I'm an economic geologist by training, and one of the challenges you've got is people burnt their fingers and spent lots and lots of money for very little value. It's great that you can do it in 2 minutes now, but looking at what you've done, it's very much about, yes, it's good to do the geochemistry, but then the problem is when you then mine it in a blast, you've got such a mixture of things, and the plant can't be tweaked that much. So, you know, these are some of the problems you've got of getting it in the system. And then secondly, a lot of the challenges you've got have been solved by people like Cisco in Australia. They've done core logging RGB, and they've figured out how to identify, you know, a core block. So have you spoken to some of the commercial people? I can help you with that. I've got a lot of connections.
We were in Australia last month, actually, so we're certainly speaking with them. And yes, a lot of people have solved various ones of these problems. Burnt fingers is a really good point. I think it's good that you raised that. Especially, you know, when you get a wave of hype, then there's people who potentially buy scanners or apply things to minerals that hyperspectral data can't see, like sulfides, for example. So I think that's why it's really important to communicate that A, sometimes this is a bit complicated, and B, that you can see fairly specific things, and if that's relevant for your problem, so like in this lithium deposit that I mentioned, the lithium is hosted in a mica, which is quite spectrally distinctive. There's nothing else that looks like it in the deposit, and so you can get quite good grade estimates directly from that. So it works really well there. Doesn't mean I would go using it everywhere. So you need to get the right tool for the right problem, and certainly when you hype things, then people get burnt fingers because they don't. What was the second part of your question?
The fact that, the geometallurgy side, you
Yes.
sample it to great detail.
Yep.
When you're blasting,
When you blast, everything moves around. Yep. This is something else where this can be, for the right type of deposit, for the right type of feed, can be useful, is that firstly, because you can apply the same technique on scanners, there are people thinking about putting these cameras on diggers so that they can actually see the blast piles and make decisions based on that while you're moving the material. And then secondly, there's quite a lot of people who are building hyperspectral sensor sorting systems. So where you have your crushed ore coming into a plant, and you can start using information on, say, how much clay there is, just to start separating different material streams. So that's a way of using the same technique in a very different context, but can help get around this problem when you move all your material around when you blow it up.
Thanks. I was really intrigued by the app on the and how closely it matched the core. Can you bring in other data sets at the same time that are collected separately, I guess?
So I guess I'll say here that app is a prototype, so it's not something that I would suggest that we can use, but it's a nice proof of concept that the augmented reality technologies that you now have in iPads can position yourself really accurately relative to the core box, and if you have a georeferencing way of then lining up your image data with that, then you can overlay it very, very accurately. It all comes down to how you build your coordinate systems. We considered overlaying things like assays, which are co-registered with respect to depth. That gets a little bit trickier because it means you need to predict the depth along the core. So you need to pick the top left corner of the box, if that's what this particular site was using, and then estimate distances based on that and see how many cores you have. So it quickly gets complicated, but it's doable.
That's exactly what I was wondering about for working with the ICDP MDIS system, which is not using depth. So it's,
Yeah, depths are tricky.
Just as a point of information regarding mineralization, I had a student look at Platreef core from the northern limb because a lot of the platinum minerals seem to be associated with sulfides and also with alteration. So we used hyperspectral scanning of the score of the core alongside grade data that had already been analysed. We picked up some of the zones of mineralisation, but let's say it wasn't a successful technique.
Yeah, well, that's good to know. And I guess that comes back to getting the right problem for the right technique. If you have questions about that alteration, then that's useful and it tells you something. If you just want to know where the platinum is, then do an assay. Yeah.
Great. So I don't know if there's any questions online. No? Scared everybody off?
How would we know if there is?
Okay. All right. Well then, thank you very much. And if no one else has any questions here, I'll close off the Geotalk. Thank you, Sam. It is about to die.